All right, welcome. In this video, we're going to be talking about the inverse of a function. So I'll start you off with the definition. Okay, f inverse of k, where k is just some number. Generally, like it's a y value that f has achieved. F inverse of k is the set of all solutions to the equation f of x equals k. So I'm just going to annotate this a little bit. Remind you that when we see f to the negative 1, that we read that as f inverse, and it really, unfortunately, doesn't really have anything to do with the negative 1 power being like 1 over the thing. It's kind of an unfortunate nomenclature in my opinion. But what you'll know is that when you're tasked with finding f inverse of a number, the first thing you're going to do is set f of x equal to that number. So let's work a little example. So we're going to let f of x be x squared plus 1, and we're going to find f inverse at a few different y values. Okay. And so what we're doing here, at least with the first one, I'll do this one for you, find f inverse of 5, we're going to set f of x equal to 5. Okay. And we've got a formula for f of x that's x squared plus 1. And we can solve for x, right? Because it's the set of all solutions to the equation, and solutions would be x values here. So what we're going to do is we're going to subtract 1 from both sides and say that x squared equals 4. And I think this is the type of equation we can solve with our eyes. We can think about this. What numbers can I square to get 4? That would be 2 and negative 2. So I'd say x equals 2 and x equals negative 2. And as a result, okay, f inverse of 5 is going to be the set of all solutions. So it's going to be the set that has negative 2 and 2. I'm not really concerned with the set notation or the set theory here. This is an algebra class, not a set theory class, right? So I'm going to say f inverse of 5 equals negative 2 and 2. Okay, but if you just wanted to say negative 2 comma 2 and not put the curly braces around it, I'd be just fine with that. Okay, so the moral here is that, you know, the inverse, it can pull back more than one x value. Okay, the inverse is not always a function itself. Okay, but then let's try these other two. I think that, you know, if you just try to approach it the same way I approached this one, you can find these things. Okay, now in this one, there's a little bit of trickiness there, but try this on your own. You know, pause the video, and then, you know, in a few seconds, I'll just bring up the answers. All right, there you go. So for f inverse of 1, I did the same thing, set f of x equal 1, solved, got just 0, and so f inverse of 1 equals 0. But then f inverse of 0, this led me to, oh, whoops, I wrote this wrong. X squared equals negative 1. I drew the right conclusion. I did this one twice in class. And so if there's no real solution, f inverse of 0 is the empty set, is what this thing means. We could also say in this class especially, we could say f inverse of 0 doesn't exist. Okay, and so what we're really doing here, before I move you on to the graphical and tabular examples, what we're doing here is we're taking a y coordinate and we're backtracking to see what x got us there. That's really the idea of an inverse function, is it just goes backwards. And so to give you a little bit more of an idea of that, we're going to look at a graph and compute some inverse values. So f inverse of 3, let's start with that one. Maybe I'll do that one in blue. So I'm tasked with finding f inverse of 3. So I'm going to set f of x equals 3. Okay. Then f of x, that represents the y coordinate. So I'm going to go up here to 3, and I'm going to like scan side to side and look for some graph. It's the exact opposite of what we do when we're like looking and trying to find the value of a regular function. We go on the x-axis to find the input, and then we go look up and down to find graph. We're doing the opposite. We're backtracking what x gives us y equals 3. That's going to be x equals 2. Oh, whoops, that was probably not a good choice, but oh well. I'm not going to be able to do that for the other ones, but maybe I'll find a way. So x equals 2, meaning f inverse of 3 equals 2. Okay. Then for f inverse of 0, okay, we're going to have more going on here. Okay, f inverse of 0, that's where f of x equals 0. Okay, that's where the y coordinate 0. That's going to be here and there, and also over here at 5. Okay, I forgot that one in class, but it is equal to 0 there. Okay, so that's going to happen at x equals negative 1. X equals, now I know that's going to be 0.5 because it's going from 0, negative 1 to 1, 1. So it's going to be a slope of 2, meaning it's gone up by 1 when it went over by a half. X equals a half, and also x equals 5. So f inverse of 0 is going to be the set that has all three of them, negative 1, 1/2, and 5. And then the last one, I think f inverse of -1, maybe I'll let you think about that. What's that going to give you back? This one could be a little tricky, I guess. So you're asked to find f inverse of -1, so you're going to set f of x equals -1. Go over here to the y-axis. Okay, there it is, right there. And what x is this? This is x equals 0. So I'd say x equals 0, and f inverse of -1 is equal to 0. And then if we were given, say, a table of values, we need to be able to do this as well. So I could go over here and I'd say, all right, f inverse of 5, I'm going to set f of x equal to 5. When we're reading a table, okay, these are the values of f of x, so I find x equals 5. Okay, there it is. I backtrack to what x got me there. That's x equals 1. So I'm going to say f inverse of 5 is equal to 1. And I could find g inverse of 5 doing the exact same thing. So maybe I'll let you think about what you expect that to be based on the table, based on how I found f inverse of 5. And that's probably enough time. If we're asked to find g inverse of 5, we're going to say g of x equals 5. We're going to go over here. We're going to find it. There it is. And we're going to backtrack to the x that got us there. That's x equals 3. And so g inverse of 5 is going to equal 3. Now I'd like to go back to that algebraic example. Okay, that equation, like we've solved that type of equation so many times in this class, we could probably just develop a rule to solve it for any y value here, right? We did 1, we did 5, we did 0, and even in this class we found that there were some imaginary solutions to that equation. We can solve this for y, okay? Or we can solve this for any value of y, we can solve for x. And that's kind of my main message here is that, finding an inverse is really just solving for x. And so there's going to be a lot of solving for x on the homework tonight. Okay, so what I'm going to do is I'm just going to try to access x on its own using techniques that we've done already in this class. So if I'm trying to get it by itself, I need to get rid of that plus 1. So I'm going to subtract 1 from both sides. And I'd say x squared equals y minus 1. Okay. Then I'm going to take the square root of both sides of this equation. Now, you might be remembering, oh, okay, when I take the square root of both sides of an equation, I need to remember the plus minus. But I think it's been long enough that I should remind you of why we do that. Let's add a different color, and I'm just going to remind you that the square root of x squared is equal to the absolute value of x. So really what I have is the absolute value of x equaling the square root of y minus 1. And if the absolute value of a number equals that square root, then that number is either the same as the square root or it's the negative of the square root. And so that's why we would say the square root of x squared, x equals plus or minus the square root of y minus 1. Okay? So I can show you right now this inverse on its own, thought of as a function that takes in y's and gives you back x's, it's not actually a function because it wouldn't pass the vertical line test from Algebra 1 because I've got two different output values for every input value, or at least input values where y is greater than or equal to 1. But I'll have more to say about that here in a minute. This is what we're talking about, a rule to solve x squared plus 1 equals y for any value of y. So if you were prompted with, hey, here's an equation, give me a rule that gives x in terms of y, it'd be this thing that we're looking at right here. But now I think, okay, we're going to talk about actual, two functions that are inverses. This is really the thing that they have dictated we need to talk about in Algebra 2, is that when f and g, two functions are inverses of each other. Two functions f and g are inverses if when I compose them, I just get back to x. Either way, okay, I need to be able to compose them f of g and g of f, and both have them basically do nothing to the function. But I'll draw you a little diagram of that here in a second. So what we're going to do is we're going to show that these things are inverses, and we're going to justify our answer. So all the prompts on the quiz and the test are going to be like, hey, determine if these things are inverses or not, and justify your answer. And how we justify our answer is by checking f of g of x and g of f of x. Okay, that's important. So I'm going to start with f of g of x, okay, using that composition of functions skill that we learned about last time. So wherever I see x in the formula for f, I'm replacing it with g of x, preferably in parentheses. So I'm going to take g of x, and I'm going to square it, and then I'll add 1. But I already have an expression for g of x. That's the square root of x minus 1 squared. And then I'm still adding 1. Okay? When I square the square root, I'm just going to have x minus 1 plus 1. And then that's just going to be x. So I'm halfway there. Okay, that's a good sign. That means if I, basically take an x value, plug it into g, and then plug it into f, which is the reverse of g, I should get back to where I started. That's what we're getting at here. But then I'm going to need to check g of f of x as well. I'm going to do the same thing. Wherever I see x in the formula for g, I replace it with f. Okay. And so that's going to be the square root of f of x minus 1. And then f of x is x squared plus 1. And then that's going to be equal to the square root of x squared, which I know I did just tell you is equal to the absolute value of x, but let's kind of think about this. G of f of x is only defined when the thing I'm putting into, so g is only defined when the thing I'm putting in is bigger than or equal to 1. And so I need f of x to be greater than or equal to, I'm not exactly seeing what the fine print is here, but in this case, okay, we can say it's x. And for this type of problem, if we can show it reduces to something like x, that's going to be good enough to show that they're inverses. I feel like there was something else I was going to say about this, but I think it'll be all right for me to move on. Yeah, let's graph and write the inverse of a function. Okay, we already have verified what the inverse for f of x is. We just did it up here. X squared plus 1 and the square root of x minus 1, those are inverses of each other. So I'm going to say, I'm going to graph, maybe I'll graph in blue, f of x equals x squared plus 1. We know how to graph this thing. Okay. Oh no, whoops, it'll go up 1 over 1, and then up 2, over 2 up 4. Okay, so it's going to go out of my window before it gets to 2. Okay. Otherwise, standard parabola. Okay, I can get rid of that dot. That's not part of my graph. Okay, but then I'll be interested in graphing also f inverse of x. And I'll be honest, I don't love the f inverse of x notation because it kind of misses the point of what an inverse is. It takes y values and gives you back x's. But this is something that I need to show you about. So what we're going to do, and I'll show you more about this specifically, that f inverse of x is this minus 1. We also know how to graph that. Okay? The square root of x minus 1. Okay, and let me think about what I'm trying to say here. I guess. So what I really want to say is, I want to go back to when we solved for the rule. Okay, x equals plus or minus the square root of y minus 1. Okay, I think in my class, I'd be more likely to say that f inverse of x equals plus or minus the square root of x minus 1. Because this is the inverse function. Okay, this is an inverse function that takes in y and gives you back x. So really what we were doing is say, okay, f inverse of y equals plus or minus the square root of y minus 1. Okay? And we could do a kind of composition of functions like substitution, f inverse of x. I'm just going to replace y with x. But what I'm saying here is that this expression here is only defined when y is greater than or equal to 1. If y is less than 1, then I'm going to be taking the square root of a negative number, and it's going to return me something complex. So what we're seeing here is that, okay, the domain of the inverse, y has to be bigger than or equal to 1, is actually the same as looking at the range of the original, right? Y equals x squared plus 1, well, that's never going to be less than 1, and we can even see that in the blue graph. Okay, so really, if I did plus or minus the square root of x minus 1, throw that in there, I'd also have the negative square root. And that's also something that we graphed in this class. We just didn't spend as much time graphing it. So I'll try to make the lower half. And then you'll see, okay, that really what's happening here, okay, I think that's as far as I'm going to be able to draw, is that the graph of the inverse of a function is equivalent to reflecting it across the line y equals x. And that's a characterization that you'll see frequently of an inverse function, but I think that of all of the characterizations of an inverse function, it's the least useful. So I'm going to move on and show you about solving for an inverse function algebraically. So if you're just confronted with a function and asked to find its inverse, what we're really doing here is just solving for x. There's a variety of ways we can express our answer. I'll show you a few of them. Okay. The most important thing, though, is the idea that we're solving for x. And so we're going to do that by probably rewriting it as y equals 8x to the 3 plus 1, because who wants to carry around f of x? That's just like a lot of writing. So I'm going to say y equals 8x to the third plus 1, and I'm going to try to solve for x, try to access x on its own on one side of the equation. So I'm going to subtract 1. I'm kind of going in reverse order of operations, so like PEMDAS, I need to get rid of addition and subtraction first, then I'll get rid of multiplication and division, like that 8, and then I'll get rid of exponents at the end. Okay, so I'm going to divide both sides by 8 because I've got 8 multiplied by x cubed. So I've got, maybe instead of dividing y minus 1 all by 8, I'm just going to multiply it all by 1/8. And then I could solve this equation by taking the cube root of both sides, because that's what undoes a cube. Okay, so I'm going to say x equals the cubed root of 1/8 of y minus 1. And if you wanted to simplify that by, I don't know, taking the cube root of 1/8, that's something we can do. But we don't need to. And I would say that this is a sufficient characterization of the inverse of f. Okay? It's a rule that gives you x in terms of a y. Oh, and I probably should point out, like, hey, you might be sitting there wondering, like, what happened to the plus minus? And when we take the cube root of both sides, we don't need a plus minus because the cube root of a function is unique. And the cube root of a negative number is a negative number. The cube root of a positive number is a positive number. It's really the uniqueness about it. I don't need a plus minus. Okay. If you're still confused on that, come talk to me. I'd be happy to discuss cube and cube root with you. So I've got all this, and that's going to be a perfectly fine characterization of the inverse. Okay. We could also say f inverse of y, because this is a function of y, equals the cube root of 1/8 of y minus 1. And then kind of in the next one, you'll see, like, sometimes the prompt says find f inverse of x. I don't just love that, but we can do that by finding f inverse of y and then just exchanging y with x. So f inverse of x is equal to the cube root of 1/8 of x minus 1. And that's us finding an inverse algebraically. But before I move on and do one more example, I want to just point out that, at least in my class, for the prompt find the inverse, any of these three would be an acceptable answer. Okay? It's only when they say find f inverse of x that we have to go all the way to that last step. All right. The last example I've got for you is one of these where it's like, okay, find f inverse of x. And I couldn't let you go without bringing back the log and exponential situation, because this is just like cube and cube root or square and square root. This is one of our clearest situations of an inverse function. Exponential and logarithms, like, they undo each other. I think it might be helpful for me to copy in that fundamental identity from when we were studying logs. And so we've got these, we knew about these. And you can kind of even see in here that composition of functions coming back x, right? We've got an exponential and we plug a log into that exponential and we just get back x. We've got a log, we plug in an exponential and we get back, just x. And so that's what I'm talking about here. So when we go to find f inverse, I'm going to start by, change f of x to y. And then just solve for x. Okay. And so with that, we can do that. So y equals log base 2 of 3x plus 4. Okay, so first, I'm going to have to start on the outside. I'm going to have to get rid of this log with base 2. So what I'm going to do is I'm going to take 2 to both sides power. I'm going to use this property here. So I'm going to have 2 to the y equals 2 to the log base 2 of 3x plus 4, which is just going to leave me with this 3x plus 4 on the right side. So I've got 2 to the y equals 3x plus 4, and now our job's a lot easier. We're just going to solve for x the old-fashioned way. We're going to subtract 4. So 2 to the y minus 4 equals 3x. I could divide both sides by 3. I could say x equals 1/3 of 2 to the y minus 4. Okay. That means that f inverse of y equals 1/3 of 2 to the y minus 4. And as a result, I could conclude that f inverse of x equals 1/3 of 2 to the x minus 4. And so just to really emphasize, when the instructions say find f inverse of x, I'm going to need to go all the way to, solving for x, saying that's f inverse of y, and then making that substitution. And, I was thinking about doing another example where it was exponential and we were finding the inverse. I'm already over 20 minutes. Why not? Let's just do it. All right, so if we're confronted with an exponential, like g of x equals e to the 2x, and we're tasked with finding g inverse of x, what we're going to do is we're going to, just like before, replace g of x with y, and then attempt to solve for x. Well, if I'm trying to get a variable down out of an exponent, I need to use a log. And so I'm going to say, all right, I need to take a log of both sides, and the log needs to have base same as the base of the exponential. So it's going to be log base e, that's natural log. So I'm going to say natural log of y equals natural log of e to the 2x. Throw some parentheses around that, make it look nicer. Okay, but natural log of e to a thing is just that thing. That's one of our fundamental identities. So I've got natural log of y equals just 2x. So I could solve for x by dividing both sides by 2. I could say x equals natural log y divided by 2. Okay, so that's an inverse relation. We could say f inverse of y equals, that's g inverse of y. Oh no. That's going to equal natural log y divided by 2. And so then I could say g inverse of x equals natural log of x divided by 2, and I've got a formula for g inverse of x. All right, yeah, that's going to be all for this video. I think you should definitely do a lot of practice on this, solving for the inverse, because that's something I'm going to ask you to do on quizzes and tests. Be solving a variety of types of equations, not just square root, cube root, exponential, log. We'll look at all of the function types we've encountered this year. All right, so that's all for this video. Thanks for watching. Hope it helped.